So we are back. Okay, good, Mariam. Okay, I think
with the presentation.
That was fast.
Yeah.
I think you should start all over again, Mariam, having your 15 minutes starting from now.
Sorry, Mariam.
Okay, it's all right. I was in the very first page anyway. Thanks.
Sorry, thank you. Thank you all.
Thank you. No problem. Okay, so the reason behind this this research work was really because of the existing challenges we've got in terms of implementing appropriate technologies to look at the integrated sustainability assessment and evaluate the environmental footprints and energy consumptions and all the aspects of the ISA in True Life Engineering Services, and also looking at the different stages of the True Life Engineering Services and see how we can make the product lifecycle more effective in terms of the sustainable design service, and also estimating the remaining useful life as well as the remaining sustainable life. So let's remind ourselves about the description of the test based on the ATI document and task 280, which I'm sure few times we've had from the different talks in this conference. Tests can be described as a set of engineering knowledge, tools, and technologies to ensure the assets are designed, developed, operate, and serviced and phased out at the optimum whole life cost. So there are four measures and attributes which are important to consider in tests, which is the availability of the asset, the reliability of it, the quality of the service and the products, and also the whole life cost. If you're looking at the literature, when we are talking about the sustainable development, the very first famous, well-known description of the sustainable development comes from Brundtland in 1987, which described it as the development that meets the needs of the present without compromising the ability of the future generation to meet their own needs, which is very important to stick to this description when we are going to talk about integrated sustainability assessment. Then we have the definitions for the triple bottom line from the Ellingson in 1994 that describes the three pillars of the sustainability as an economic, social, and environmental. And to assess this, we've got the integrated sustainability assessment methods and approaches that looking at to how to identify and evaluate the effect of the parameters, functions, policies, and different regulations on sustainability. So in terms of the three pillars, if you're looking at the environmental assessment, we are going to focus on evaluating the energy, the material consumptions, and also the different emissions, and also trying to minimize the needs for the water and fossil resources and natural gases. In the economic pillar, when we are going to assess the impacts of it, we are going to estimate the prosperity and profitability of organizations and individuals. And in a very nutshell, when we are going to looking at the social assessment, we are going to measure the social and psychological impacts of the organizations and individuals. So now if you are going to see what are the potential impacts, the test impacts on the sustainability, if you are looking at the economic pillar, potentially tests can support the sustainability in terms of reducing the design and maintenance cost, reducing the rework at the both design and manufacturing stages, or spare optimizations, logistics optimizations, and improving the product availability, reliability, and predictability. In terms of the environment pillar, tests can looking at the reducing the material usage and waste, reducing all the activities throughout the product life cycle to also minimize the fuel efficiency and extending the product lifetime, and minimizing all the disruption costs might happen during the product life cycle, and also reducing the natural resource consumptions, the energy consumptions, and looking at the net zero carbon footprints. And in terms of the social, potentially tests can looking at the working conditions, health and safety, culture, safety, security, consumer privacy, fair salary, and working hours. So this leads us to the research question, to coming up, what are the sustainability opportunities for the integrated sustainability assessment throughout the product lifecycle? So as I mentioned, this research is purely based on the literature review. So as the first steps, we look at, we conduct a systematic review to examine the existing literature regarding the sustainable development in product lifecycle. At the second stage, we, based on the findings from the literature, we mapped, we create a mind map that present a holistic view of tests in integrated sustainability throughout the product lifecycle. And finally, we come up with the test opportunities in ISA, and also a set of recommendations for further research and studies in this field. So at the very first stage, the systematic review. So at the very beginning, to identify the literature, obviously this is a very vast topic. Test covers a very different topics in this area, and we come up first with around 1,464 papers, and at the screening level, we identify some of the papers who are not very relevant to the topic that we are interested. So we eliminate, exclude around 600 of them, and then after going through the eligibility exclusion, we end up with 46 papers to fully review for this research work, which these 46 review documents include 25 journals, 9 conference, 3 book chapters, and 9 other scholarly documents, as well as some of the standards published in this area. So this is the outcome from the systematic review we've done. So we've looked at tests. So we look at the develop phase, prepare phase, utilize phase, and the retire. So at the very first phase, we come up with the key elements in terms of the integrated sustainability opportunities, in terms of, for example, design for X rhythm, and also design for life cycle, eco design, and design for sustainability. And in terms of the prepare stage, we come up with some of the elements such as flexible and agile manufacturing, additive manufacturing, mass customization, reconfigurable manufacturing. At the operation stage, servitization is key elements when we are looking at the integrated sustainability, the PSS customization, sustainable remaining life, and also looking at a more predictive and condition-based maintenance and remote maintenance. At the final retire stage, obviously the first things is circular economy for tests, and also the service chain optimization, reverse logistics, looking at the 6R principles remanufacturing. And some of the elements with regards to the integrated sustainability opportunities lies within all these 4 phases through the product life cycle. The first one, life cycle costing, equality, diversity, through life value co-creation, and resilience in products and service, which also come out of the discussion with the keynote with Andy Neely this morning, that these are the areas that we should focus on, the value co-creations and also the resilience. the Industry 4.0, the net zero carbon, and so on and so forth. So these are the key topics that we identified in terms of the integrated sustainability opportunities for TESS. And now at the final stage, what we've done is now we've tried to map it against the 3 pillars of the sustainability. So we look at the economic, environmental, social, and also the correlation between all these economics, and see how these topics in the literature, how these elements would sit in all these pillars. And as you can see from this matrix, as far as we are moving toward the social aspects, we can see that there are less works and less considerations toward the social aspects, and also the correlation between the social and, for example, environment. And these maps leads us to coming up with some recommendation that we can have for the future research and future studies and works around the integrated sustainability assessment for TESS. So lots of studies has been done around the design for X-Realm. However, because TESS would looking at all the feedback loops and all the updates through the product life cycle, updates from the design to manufacturing, manufacturing to service and end of life, and also get all the feedbacks through the rest of the manufacturing phase and design phase. For this bit, we can also looking at some of the aspects such as design for end of life, manufacturing for service, or manufacturing for end of life, and so on and so forth. Second, as we understand, the social and environmental aspects with a bit less focused of the test. So working on the remaining sustainable life of the components, and finding a more environmentally and social friendly tools and technologies for tests could be as part of the future research. And also when we are looking at the Industry 4.0, again, we can looking at how we can look at the social impacts and environmental friendly technologies. For example, looking at the human factors and also human-machine interactions. And further studies can be carried out for the service design for sustainability, for sustainably manufactured product, such as, for example, design the service for additively manufactured product. So we've got the additive manufacturing, now how we can design the service with regards to the sustainability. And also looking at the life cycle assessment when it comes to the PSS and servitization. And also looking at the correlation between the social and environmental opportunities in TESS. And of course, at the end, if we can also carry out more research around the triple bottom line metrics in TESS with a view to evaluate their impact on the asset availability, reliability, quality, and cost, which is really the aim of TESS. So to conclude this, because of the frameworks has been published in TESS 280, we can realize that if we are going to take the TESS approach, we are having a continuous feedback of experience in tests that informs the design, prepare, utilize, and retire. And because of that, we are thinking that in contrast to the traditional research in product lifecycle sustainability, tests can provide a more robust sustainability in that manner. And that would end my presentation today. Thank you, and I'm open to any questions.
Thank you, Marianne, for your very nice presentation. From the audience, we have got one question already. Is it possible for you to read that question? And also for the audience to read that question from Mr. Keith Rushton? If you...
I can read it.
Okay. Yeah.
Myself. Past 280 is trying to bring focus on the support activity assets, which by cost accounts for 60% of the whole life cost. How far is your research looking at these associated support activity assets? I suspect they may actually be responsible for a large proportion of the sustainability issues. Yes, that's absolutely correct, Keith. This research was really aimed to identify the area that tests can work further. So I think this is like a further work to this research now we go to these elements individually and see how the test framework can identify the tools, technologies, knowledge and information to fulfill this.
Okay, thank you for your answer. I myself have got a question regarding what you mentioned in almost the last slide, and also I was going through your paper in the proceedings, and because that corresponds to what you wrote in the conclusion section of the paper. That is, you are saying that TESS approach is more holistic or more robust as compared to traditional product life cycle approach. I wonder, there are many people that argues against that kind of statement, saying that life cycle is holistic as such. And so by life cycle perspective, one can cover different issues against a functional unit on question. So could you elaborate a little bit what are basically the fundamental difference between the TESS approach and the traditional product lifecycle approach?
Well, I don't think in terms of looking at the product lifecycle itself, the test would be any difference from the product lifecycle. Okay, so the way that we are thinking that makes it more robust approach in terms of the sustainability is test is not just looking at the asset itself, it's also the product and the service. It's also looking at the different tools and technologies, knowledge, information that should be provided to support all the stage of the product life cycle. And because it is a kind of integrated of all these infrastructures, let's say, we believe that having a continuous feedback between the design of the products to the design of the service, to design of the technologies, to design of the way that you are maintaining and repairing the asset, and so on and so forth, would makes it more robust. However, this is a hypothesis that definitely need a further research and works to test it, to validate it.
Yeah, thank you. But maybe this is a matter of terminology that are used. I understand what you are saying is basically product service system. That's my understanding, and which is quite widely used in literature. And I know, of course, there is a term and associated concepts for tests through life engineering service. But yeah, that's a comment.
Thank you, John.
Thank you, Mariam. Being cautious of time, I would suggest that we move on to the next presentation. So the next paper has the title of Feedback from Remanufacturing, Its Unexploited Potential to Improve Future Product Design. And it has been authored by Louise Haziri, Eric Sanding, and our co-chair in the session, Tom Sakao. So with no further ado, may I invite Professor Tomohiko Sakao to present. The floor is yours.
Thank you. So I'm going to share with you today the result of our research that has been already published on the Sustainability Journal. The the paper was written with Louise and Eric, my co-authors, at the same department of Linköping University in Sweden. Oops. So this paper talks about remanufacturing. I use the term reman for short. It can be defined like this. And it's actually an important component for example, for circular economy, as you can see on the butterfly figure by Ellen MacArthur Foundation. If I reformulate the butterfly diagram to a more process-oriented description, we see different processes in the product life cycle, and between different processes there are material flows in the levels of material component products. But what I want to emphasize here is that there is a process that is design, and design is unique as compared to these processes because it is the process that doesn't sort of exchange materials rather, but influences through information on the other phases of the life cycle. Therefore, there are many concepts represented by Design for X, and this presentation concerns Design for Reman. So we aim to analyze the information flows from Reman to product design as a specific objective of this research. And we set up 3 research questions. Number 1, we look at the potential flows of information from Reman to design theoretically. And then we looked into practice regarding what are the barriers and also enablers for that information flow. So as a method, we used literature review in order to look at the theoretical information flows, while we used multiple case study at industry, and we eventually combined the outputs from the theoretical part and practical part. In looking at the practice in industry, we communicated with 3 OEM, original equipment manufacturers, that have rather long history of remanufacturing. All provide complete products with different levels of complexity. Case A provides food processing machines. Case B provides material handling products, and Case C provides office furniture. So basically, we interviewed a number of different staffs from each of these companies, including design and remanufacturing and other departments. This slide shows the results from literature review regarding the potential information feedback from Reman to design. You can see that at the bottom of this table, and in order to compare that with other information feedbacks, I mean from other phases such as manufacturing and use and services, so I show that information together in this table. So as you can see at the bottom concerning Reman, there are different types of feedback in terms of contents and also sources of the information, such as data about the Reman process as such, and the data that the personnel, Reman personnel has, and so on. This slide shows the results of the multiple case study looking at the practice of information feedback from Reman to design. And in the same way as the previous slide, I am showing the equivalent information from manufacturing, use and services to design phase. As you can see at the bottom concerning Riemann, on the right-hand side, you see no information feedback or very little from the 3 companies that we studied. So basically, this shows a very strong contrast with the feedback from manufacturing and use and services, as you can see at the upper parts of this table. Concerning barriers and influencing factors as enablers, we can say that based on the literature and also the interviews, both, we can say that the organizational structure can be a barrier for supporting the information feedback from Riemann to design. Other barriers are lack of feedback channels, lack of incentives, lack of Riemann knowledge, and lack of awareness of Riemann as such. But on the other hand, you can see 3 factors that can function as enablers, such as customers' demand, managerial decisions, and laws and regulations that can support to overcome these barriers for the feedback from Riemann to design. Oh yeah. This slide elaborates a bit more for the enablers, and it highlights also design process, that is integrated design process is also highlighted. New technologies as well. So I'm now trying to sum up with the discussion of the results that we gained from literature review and multiple case study with industry. So basically this slide depicts the sort of information feedback from production and material production or component production and the final product assembly to design. So this information flow has been much researched in literature, as well as we could observe these flows in the 3 case companies. This makes sense because the aim of DFM is to reduce manufacturing costs that are borne by this OEM as such, these OEM as such. So because if, actually this is a key determinant, especially in the new manufacturing, because they can save costs, thereby they can increase the profit. In the same way, we can find a lot of knowledge in literature, and also we can see the practices for the feedback from service/maintenance to design. This also makes sense because design for service aims to reduce service costs that are borne by this OEM, because this OEM also provides services as well. And also it improves the reliability of the product and also availability. But as you saw in one of the previous slides, there is very little feedback from Riemann to design. Riemann aims to reduce Riemann costs in the same way as DFM and DF service, but as far as the 3 case study companies are studied, this cost for Riemann is not really a key factor for the entire business of the 3 companies that we studied. So one factor is, of course, the scale of Riemann, meaning that the three companies have rather small portion of getting from Riemann as compared to the whole revenue of the companies. And also we found that in some cases organizational structure hinders the flow of information from Riemann to design. To conclude, as I have already mentioned, even though the three case companies have long history of doing Riemann in their business, we found almost no feedback from Riemann to design, and also no structured method or sort of active requests for feedback from design to Riemann, so that design people can get information from Riemann. So future work, in order to facilitate Riemann, we think it makes sense to investigate a method to integrate feedback from Riemann into the design process. I hope this is interesting to you. These two projects supported this research. Thank you very much. Any question I would like to try to answer.
Thank you very much for this very interesting presentation. I've just got one question. One of the challenges that most of the companies are facing with regards to remanufacturing is designing when to actually schedule that remanufacturing within the life cycle of a product. During your interviews, have you had any insight from these companies? Would you be willing to elaborate a little bit more on this point?
Yeah, could you, is it possible for you or the person who made this question clarify a little bit more? Was it, the question is about when Riemann related decisions are made? Is that the question?
Yeah, that's the person who did that question is me, basically. So
yeah.
yes.
Okay, yeah, let's assume so. Because the sort of intention of this research is what has been such decisions. We sort of assumed such decisions are being made in the design phase. So that was a sort of starting point. And then we found this kind of results. So to answer to that question directly, the decisions are not really made, at least in a systematic way. So basically, the cores, basically the used components or products, come back when the products are sort of product lives or contracts, leasing contracts are finished. And basically, the people in the Riemann department sort of react, work in a little bit reactive way. So that's the sort of overall picture.
Okay, there is one other question in the chat. Keith is asking for a little bit your insight based on your experience on what are the major differences between repair and remanufacturing.
Yeah, yeah. I can just try to show the definition that we used for this research. So repair doesn't necessarily bring back to the near original state. So Riemann states that Riemann brings the cores or products back to like new, meaning near new or even better state, condition, quality. But repair can, at least in my terminology, repair aims to bring the products back to a sort of functioning state, which doesn't mean the quality is back to the near new state. So meaning that we sort of accept the quality is degraded because of the deterioration or whatever. So that's at least what I see as the difference.
Okay, thank you very much. Being cautious of time, I would suggest that we move on to the next presentation. So if you just please stop. Okay, perfect. Thank you. So the next presentation is going to be delivered by Mr. John Patsavelas, and the topic of the presentation is on the use of carbon nanotubes and graphene radiant heater printed on flooring substrate, and he will be running a feasibility study. John, if you please switch on your camera and share your screen, you have 15 minutes to deliver your presentation. I think you are on mute, John.
Sorry. Let me share my presentation. Please bear with me. Okay. Okay, so good afternoon, everyone. I'm John Patsavelas. I'm a senior lecturer in manufacturing management in Stanford University, and I have presentation to share with you with regards to a paper we've written on carbon nanotubes and graphene radiant heaters. This is a feasibility study that has been completed not very long ago. If you don't mind, let me just change cameras a little bit. Oops, nope, doesn't work. So apologize. Perhaps that's better. Okay. The motivation for the paper has been the opportunity of decarbonization and the alleged size of the prize. Recently, reports have been written, one from the Machines Technology Association, Manufacturing Technology Association, that the effect of new technologies into UK manufacturing is purported to be quite large, and that involves getting a lot of things right, constructing government policy, and within a broad regulatory framework, government can provide enabling assistance by nudging the direction of change and facilitating space. And you can do that through regulation, and this is a relevant context here. The UK has enshrined in law in June 2019 to achieve 100% reduction of greenhouse gas emissions to net zero by 2050. Crucially, the UK government has also announced its intention to ban the use of fossil fuel heating systems in all new houses from 2025. And the residential sector alone accounts for 15% of all greenhouse gas emissions. This is equivalent to the whole of the UK's power generation greenhouse emissions. So it's a very large part of the issue that the UK country has to approach. Considerable challenges and opportunities arise for new sources of energy, such as hydrogen and electric heating, and using clean energy for retrofitting existing housing stock in the UK and, of course, in other countries. Also, since about a month ago, the UK government has announced a target for 2030 for offshore power generation to increase by 10 gigawatts in 10 years. The UK is already the largest offshore power generator of wind turbines. So there is an element there that says that electric power is going to be increasingly derived from clean sources. So as the intention has been announced to ban the use of fossil fuel heating systems in all new houses from 2025, this presents a critical consideration. Where are those emissions coming from in the built environment? And most of them come from CO2 emissions from the use of natural gas, which is being used as a fuel is in central heating boiler installations in UK homes. And this presents a number of challenges in terms of the choice between existing technologies possible to achieve better or equivalent thermal comfort solutions to natural gas heating, time and complexity of coming up with new lower carbon heating solutions for new homes, and the costs relevant to heating of dwellings in winter times in the UK, which is about currently 60% of an average household's energy bills. So the technologies on the forefront of decarbonizing the built environment heating seem to be electricity, which is increasingly coming from cleaner sources, and hydrogen. And having looked at electricity, the current technologies taking the most attention the air source heat pumps and air to water heat pumps. But the housing stock and the built environment is a complex place. The complexity of the built environment heating would require, in our opinion, a diversity of complementary technologies that do have a reduced energy consumption requirement, have space-saving features, and easy installation methods for retrofitting. And space-saving features for new heating methods is very, very important in that environment. The paper that we've written explored the feasibility of using very thin printed layers of a mixture of carbon nanotubes, CNT, and graphene materials that can act as an electrically powered radiant heat emitter under certain built environment surfaces, such as flooring, coverings, ceiling substrates, ceiling tiles, and wall coverings in the built environment. Now, carbon nanotubes and graphene, some of the key facts. The carbon nanotubes were discovered in the early 90s. They have a number of good properties, interesting properties. Crucially, they have current densities up to a level of 106 amps per square centimeter. And then we have multi-layer graphene. Graphene, a two-dimensional form of crystalline honeycomb structure, discovered in the early noughties, and also displaying very high current densities. Now, the mixture of carbon nanotubes and multi-layer graphene with the right formulation in a dispersed ink carrier, the resulting suspension can provide a conductive printed film which can be printed on a given substrate. That printed film can act as a heater due to a phenomenon called the Joule heating, which seems to be emitting radiant heat very uniformly. So, given the need for alternative solutions with regards to lower energy and easier installation of underfloor heating in the built environment, radiant heaters could be of benefit. And printed films can be very, very thin. They have low energy consumption requirements, and the Joule heating phenomenon results in instant emissions of radiant heat energy, and that's the theory. So we went about in our lab using a formulation, creating a formulation of carbon nanotubes and multi-layer graphene, we spray painted a 50 square centimeter area of the surface on a patented cementitious board. And this is a board that has been chosen specifically for its mechanical point load benefits in the built environment, which are superior than ceramic tile. And crucially, because of its fire-resisting properties when it's used in internal and external spaces. We all know of the cladding fires of Grenfell Tower in London. The combustible materials used on those spaces don't lend themselves to a built environment. So this board was chosen for these specific properties. Our formulation consisted of carbon nanotubes, which were developed in our laboratory with the team of Christoph Koziol, and multi-layer graphene, which were sourced. And within a toluene suspension, we created a formulation which was then spray painted onto the cementitious board, creating that surface area. Using some copper channels for conductors, we then proceeded to test the printed heater. Our focus was to assess how it would perform under different values of voltage, to try and characterize its properties as a heater using a direct current source. So the experimental setup was pretty simple. We have a cementitious board through alligator clips connected to a pretty reliable DC voltage regulator, achieving stable voltage values of between 0 and 30 volts. And we had a thermal imaging camera, which was able to detect infrared radiation. Some of the results. We carried a number of experiments, in fact, more than 70, different voltage values. And we've plotted the time against temperature and voltage against temperature. And the notable effect of our discovery here is that we found that the higher the voltage, the higher the maximum temperature. That was kind of expected, but we wanted to plot the exact relationship of this specific formulation and record it. And crucially, the interesting thing here is that the surface temperature of the heating element reached 90% of its maximum temperature quite fast. Within 5 minutes, it appeared to reach its maximum temperature, and within 9 minutes, it had reached 99% of its maximum temperature. So we kind of validated our hypothesis on the fast transmission of infrared heat energy. Again, we were kind of expecting these relationships between current and voltage, and there is we wanted to assure the stability of our measurements. So these are all within 5% values of what were expected. And then we saw the resistivity values as a result of voltage. And here we can see some effects of the specific formulation that we've used of carbon nanotubes and multi-layer graphene on the behavior of the curve, which characterizes the specific formulation. The other element we wanted to see is whether the cementitious board used presented some kind of obstacle or barrier to the transmission of radiant heat, radiant heat energy, and thus we took measurements on both sides. We detected the infrared energy on both sides of the board, and we have seen that checking that pass-through of energy through the 8mm cementitious board, that we have a pretty good heat transmissibility through the body of the board. For low value voltage or value, thermal difference between the two sides drops below 3% within 3 minutes, which is considered to be a pretty good result for transmitting through the board. And we also wanted to see how far we could go. We had stability through the experiments. The experiments were pretty repeatable, we have found. And then we used to try how to find the limits, the operational ceiling of this setup, experimental setup. We've used 30 volts to assess the specimen performance under maximum conditions. The temperature reached 150 degrees Celsius within 15 seconds, and blisters started to appear on the surface of the printed film board, as attested by the infrared record here, and that's the actual physical sample. So we've established that at 30 volts in this particular formulation, we can have degradation of the heater pretty quickly. And that concludes the fact that we've established that specific formulation that we're able to create in our lab on carbon nanotubes and multi-layer graphene can be used successfully in a cementitious board as an underfloor, underwall, or other substrate heater in the built environment. Crucially, this board can go in external built environment spaces as cladding that requires heating, for example, when there is frost, when there is a wet area, and there is the danger of sleeping through frost. And certainly internal spaces like bathrooms, office environments, and certainly can be used as underfloor heating in housing stock, as well as retrofitting because of its very, very slim nature. The transmissibility of the radiant heat through the board is fast and unimpeded, so there aren't any significant reflective impediments in the material of the board. And the operational boundaries of the current formulation have been established, which leads us to the possibilities of further optimization of the formulation and enabling further experiments, as well as on the efficacy of different printed design patterns. As you see, we had a very uniform, very simple rectangular pattern. We would like to experiment with different design patterns on the printing part of the heater and measure its effect on larger specimens. And yes, that concludes my presentation. I'm happy to take any questions.
I was wondering whether Tom.
Yeah, I can take the lead of the discussion. Thank you very much, John, for your nice presentation. Well, we would like to take any question from the audience, but I don't see anything on the chat function. May I ask one question?
Sure.
Yes, I heard about a case in UK regarding heat incineration for housing. So they sort of improved the sorry. They improved the construction of the walls so that the niche between, so unintended niche will be minimized. So the heat transfer between the outside and inside, it will be minimized. But then, so that technology was successful from that point of view, and energy use for heating is of course decreased. But on the other hand, that had a bad side effect, which was sort of contributed to increase of the moisture inside the housing, so that the mold grows faster because of that. But with your technology that you mentioned today, is there a possibility of having that adverse side effect?
Yes, that's a very good question, actually, because you're talking about the quality of indoor air. And indoor air quality is a very important element for human health. It's something that has been overlooked, I think, over the years. And not only that, not only do we have issues on very highly, what they call passive houses, highly insulated houses. The trouble there is introducing new air, fresh air into a dwelling without any energy losses. And the very sophisticated systems that are not particularly affordable for normal housing. So higher level of insulations are more affordable, but introducing fresh air whilst being heat conditioned is quite expensive. And one of the reasons why prompted us to do this research, it was the cost of retrofitting low carbon emission heating solutions, given the legislation that is coming. So the government is saying, yes, we want to get rid of the hydrocarbons, yes to new ways of heating, and of course insulation plays a big role. You're right, there will be an unintended consequence there. However, our system, because it's infrared heating and it's pretty fast, if it was to be developed for heating dwellings, it would actually heat the bodies, it would heat the people of the house, of the dwelling. Because it's like, and I can give you an example of, in the wintertime when you have a sunny day and you're outside, the part of your body that's facing the sun gets warm up pretty quickly through infrared heating. And the part of you that is not in the sun, it feels pretty cold. So infrared heat, radiant heat, has that effect. It heats the body instantly, but it doesn't expend a lot of energy trying to heat the air, which means that fresh air can be introduced into a dwelling without the fear of losing heat energy as much. And that way, even people who cannot afford very sophisticated air refreshing technologies could benefit from radiant heat. Obviously, the small size of it, the fact that it could be potentially printed on flexible substrates that can be stick and lift in the backside of this board, and that board can act as a carrier to other flooring substrates like carpet, it could be wood. And because of its thermal properties, even if there was a thermal runaway, that would not result in a fire, which is very, very important in that environment.
Thank you for your answer. I'm conscious of the time, but we have got a question on the chat function. It's about waterproofness. Is it possible for you to read that question? You don't have to read up, but can you see that question?
Actually,
no. Then I can read up. Have you explored any way to waterproof this element whilst minimizing the loss of heat output?
Yes, I think that's a very good question. And the printing process that we have used is enabling the print layer to act almost as an impermeable membrane. Usually there would be an impermeable moisture membrane before you lay down such a substrate, either on the wall You can have Tyvek type of materials preventing moisture ingress, or you would have other types of moisture membranes. But there is a possibility to consider the print layer itself acting as a non-permeable moisture membrane. This is something we would like to test further as we improve the formulation on its degradation, let's say. So we would like to see how that could be achieved and achieve also that functionality. We feel that there is a possibility there, but it also depends on its printing method. Currently, the printing method that we use is quite expensive. We want to proceed to other printing methods. But certainly one of our tests will be immersing this into water, for lack of a better expression. And we're using DC, we're using very low voltage, so the chances of endangering safety are low. So thank you, yes.
Yeah, so the question the person who asked this question says back to you exactly, this is what I was thinking. So great research. So you're encouraged to continue with that. Thank you, John, very much for your nice presentation and interesting discussions. So Konstantinos, shall we close the session? So the audience is invited to go back to the auditorium. Is that correct?
At this point of time, the workshop one is still in session. So if you want to join that, please go ahead and do so. If not, the closing session will be starting 4:45 in the auditorium. Again, thank you very much for your attention. Thank you very much for your participation. Thank you, Tom, for co-chairing this session. And stay safe and enjoy the rest of the conference.
Same to the audience. Thank you. Bye-bye.
Thank you all.